Okay, so we have a little over half an hour, I guess, here. See if you guys have questions on any of the homework or any of the concepts going back to 11.4.
Sir, I have a question on number 16 for 12.4.
Yeah. Right. So let's see. So what does it say? It says you want to measure a really long distance, and what you could do is you could measure it with a short measuring tape a lot of times, or you can measure with a long measuring tape a short number of times. So I think, I mean, it probably makes sense that if you have a small one and you measure it, I don't know how many times that is. So suppose you measure it that way, or you measure with the measuring tape, sort of even just twice, same length in here. The point is each of these little times here, you will have a little bit of error. So you're gonna have like a little bit of error, and then you're gonna have a little bit of error, and then you have a little bit of error, and you have a little bit of error. And so if you have a small measuring tape, then you'll have lots of little errors. Whereas on the bottom one, you'll just sort of have few. I mean, I think that's probably about it. So we're talking about like D. What was D here? D is the total distance is the number of things you do times the length of any particular one. So when you're talking about errors, error here, then that's like delta D or D, little d, big D. So this is like actual error versus approximate error. And so you're talking about, I mean, if we just actually work this out using the complete differential, this would be the derivative with respect to n times dn plus the derivative with respect to L times dL. So this would be L times dn, and the other one is n times dL. And so it depends, it's like if these two little dn's, if this one and this one are pretty close to each other, this just means a little error in n versus a little error in L. And the point is well, if the L is larger, that was the question that, if the L is larger, then the compound from this dn, you're going to be multiplying your L times a small amount. But if your L is let's see, if your L, which one do I want here? I might be confusing myself here. I think the answer is probably up here. So if you talk about lots of little errors, then you're basically talking about many little errors, as opposed to just a few little errors that might occur at the overlap in the middle. And so that's sort of the easiest way to think about it. I don't know if you've ever like measured anything before. You only have like a ruler, right, as opposed to a yardstick or something. You measure it, but then you're like move the ruler over, and you have a little error here, and you move it, you have a little error, and they'll start to compound as you go along. And so that's basically it. I think I'm gonna just sort of, I haven't really prepared that good part there. So I don't know. It says using differentials. I think for the test tomorrow, I'm not going to worry about it too much. I think just sort of this common sense that the error will only be occurring a couple times with the long measuring stick than with the short one.
Thank you.
Sir, can you go over problem 16 for 12.5?
Okay, so just practicing chain rule here. Right. So this one says, what does it say? Given, oh, find the values where the derivative is 0. Is what it's asked for. But in order to find it, there's sort of two ways to do it. I mean, right. So we're trying to find with respect to t, but realize that z is a function of x and y, and each of those are functions of t. So the first method, you could just substitute in and get z as a function of t. So you could plug in cosine here, and you could plug in sine there, just straight up. This is like method number 1. Just straight up substitute them in before you do any derivatives. So dz dt will be quotient rule, I guess. So bottom times the derivative of the top minus the top. Crap. I think I can do this. Times the derivative of the bottom. So that'll be 2 sine times cosine. And it's divided by the denominator squared. That's like method where you just sub in first. Now, if you use the chain rule to do that, and I know in this one you probably don't want to, but just for practice, method 2, where you use the chain rule. And this is where you do this idea of you take the z derivative, or the x derivative with respect to the x derivative of z, which is a partial derivative, and the y partial with z, and then you'll do the t derivative of each of those. And then the derivative of z with respect to t will be the derivative of z with respect to x times the derivative of x with respect to t plus the derivative of z with respect to y times the derivative of y with respect to t. And so you just need to find these derivatives and substitute them in. The derivative with respect to t of x is pretty easy. That's just minus sine. The derivative, of y is cosine. So what you need to do is you need to find these two derivatives, multiply them in. Now in the end, you're then gonna have to sub in you'll have x's and y's and t's. So if you want to figure out where this thing is 0, what t values make it 0, you're gonna have to plug the x's in and y's in anyway. But these derivatives maybe are not as bad. I mean, it's not too bad. You'll have 1 over y squared plus 1 because, well, it's just x and then times some constant. For the y, you just use a chain rule, so it'll be negative 2yx over y squared plus 1 squared. So you could do a quotient rule if you want. You could bring this up as to the negative 1 power, so it'll be negative y squared plus 1 to the negative 2, and then you multiply that by the derivative of the inside. So there's a bit of a chain rule going on there. But then you're going to want to set that to be 0 anyway, so you're going to have to sub in x equals cosine, y equals sine, and then set dz dt equal to 0. So I don't know if it's easier to do it here or to do it here. They're pretty much equivalent. But if I did try to set dz dt to be 0, then I have a fraction, which is equal to 0. So how do you make a fraction equal to 0? That means that the numerator has to be 0. So I set the numerator equal to 0, and I'll get sine squared t plus 1 times minus sine minus, when you multiply this together, you'll get 2 sine t times cosine squared. And you want to set that to be 0. So I did everything right here. 2t times top times, yeah, chain rule. Just before I go to the next slide, just make sure I have on bottom through top minus top through bottom. Okay, so I have this thing, and so I don't know. Let's see what happens here. Sine squared plus 1 times sine minus sine minus 2 sine t cosine squared equals 0. I guess you could factor out sine in both. So you'd have minus sine squared t minus 1. That should just factor out negative sine, actually. So if I factor out negative sine, I'll have sine t squared plus 1. Factor out negative sine here, I'll have plus 2 cosine squared t. All right. So how do you do that? Well, we can clean up the inside here a little bit. Sine squared plus cosine squared is 1. So I could take sine and I could take one of the cosines and put that together to be 1. So I'll have minus sine t times this. I'll have 1 plus 1 plus the remaining cosine squared equals 0, or minus sine t times 2 plus cosine squared equals 0. So what does that mean? That means we have two things multiplied together to give 0. That means either the first one is 0 minus sine t is 0. And that occurs when t is 0 or pi or 2 pi or negatives of any of those, plus or minus. So that's usually written as like plus or minus, well, they'll just write it like this. Some multiple k times pi. And then the second one, 2 plus cosine squared t is 0. Well, that'll never happen because if I took a t and squared it, or took the cosine and squared it, it would be positive. So there's no answer for that. You can't square something, add it to 2, and get 0. So that looks like if I did all the pieces and didn't miss any minuses, it looks like it should just be that. Any multiple of pi. So there you go. All right, what else? Deafening silence. Right, so again, you see 11.4 was on the unit tangent vector and normal vector. 11.5 was on curvature. We also had AM and AT. We had a lot of stuff in there, but mostly it was like curvature, radius of curvature. There was the arc length parameter, but we jumped over that pretty quickly. 12.5 is just definitions of these things, domain, range. 12.2 is limits. 12.3 is partial derivatives. And more. 12.4 was on df. 12.5 is what we just did. 12.6 even. Yeah. I'm trying to think back on that 12.4 again. Piece 16. Let's see. The distance was N times L. So the total differential, which is like how much of this is, will come into play as N times dl plus L times dn. And so it's the L derivative, dl, and this is the N derivative. This is terrible. Capital D. We're using the capital D too much here. So the actual error in D, so this is like the approximate error, will be in D. This right here is it's saying, suppose that, you know, each time you measure, we're off in our measurement here by around 1/16 of an inch. So N and L, we know those. But basically the point is, I think, just looking at this term right here, is if every time we measure we're off by 1/16, then if you use the 3-foot measuring tape, you're going to have to measure, you have to measure 10 times. And so that term will end up being 10/16 of the NDL. And then if you use 10-foot measuring tape, then you're measuring 3 times, and therefore the error from that term there will be 3/16 total. So you can see that if you have the shorter tape, then the compound error that's getting added into the D is off by 10/16 total and 3/16. And again, that's just the common sense of you measure it 3 times. The worst case is you have an error and an error. And maybe you don't even need this last error, but you know, compound by missing that 1/16 3 times versus 10 times. You're killing me here. Well, let's see. So when do you guys want to do the test? Why don't you email me your choice on whether you want to take it in the morning or in the afternoon, according to the schedule. I mean, I have it written as the morning's 13.1 and the test is in the afternoon. If you prefer to get it over with first in the morning, that's fine. So just send me a vote. If you don't care, you know, just send me a vote in the next hour. I'll check it and then let you know what we're going to do. 13.1, just as a tip, is we're going to cover that either in the morning or in the afternoon. And that is using, you've been waiting for it, so doing double, we have like, you know, multi integrations going on here. So what are called iterated integrals, where you have like a dx and you get an answer, and then you take that answer and then you do dy, and somehow this gives you something. But anyway, so we'll just stop there then, I guess. And if you get the homework in, that's great. I'll have a look at it and send me your vote on when to take the test. And otherwise, go look for the comet tonight, right before sunset. So have a good rest of your morning.
Thank you, sir.
Thank you, sir.
Thank you, sir.